Good afternoon, everyone. Thank you for attending this workshop on additive manufacturing, where we intend to present you some challenges and opportunities for nuclear technologies. So I'm Stéphanie Richet. I'm program manager at CEA Energy Division. This program is about circular economy of materials. And in this program, we drive the roadmap on additive manufacturing for the energy division. For this workshop, I have the pleasure to be with Jacques Portal. Jacques is a project manager at Team Henri-Fabre. Team Henri-Fabre is a French association based in the south of France and promoting innovation with a cross-sectorial approach. And Jean-Christophe Vidil. Jean-Christophe is president of Nikon SLM France. And Nikon SLM is a key LPBF manufacturer in Europe. So here is the agenda of the workshop. I will briefly introduce additive manufacturing at CEA, and then I will present what are the opportunities for the nuclear industry brought by IM. Then Jacques Portal will present the main result of ARQANE French national projects. And then I will present you the remaining technical challenges and emerging opportunities for the futures. And we will conclude with a roundtable discussion, a short discussion starting here and then carrying on the room after if you want to join. And during this roundtable discussion, Jean-Christophe Vidil will have the opportunity to share with you the vision of a manufacturer of additive manufacturing machine on the perspective of AM. So let's start. So briefly, CEA is a research technology organization. Its missions are stated by the French government. One mission is the nuclear deterrence and the security of France. And the second mission is to create innovation, transfer it to the industry in strategic sectors such as the energy transition, the digital transition, and technology for health. And we have more than 22,000 employees. We deposit more than 600 patents per year, and we collaborate with about 7 industrial partners every year. So if we focus on additive manufacturing for civil application at CEA, it has started in the 90s, but it relies on decades of expertise on simulation, material formulation, characterization, and non-destructive techniques. There are about 100 research engineers working on this topic, and it relies on 16 platforms. So 10 platforms are generic, meaning that they are used beyond additive manufacturing. This is the case of the Janus irradiation platform or the corrosive mechanical and chemical characterization platform in CEA Saclay, or the nano characterization platform and the nano safety platform based in CEA Grenoble. And we have 6 platforms which are dedicated to additive manufacturing, such as the Samantha platform, which is based in CEA Saclay and which is focusing on metal additive manufacturing, powder and wire. And in Grenoble, we have, for instance, the powder additive manufacturing addressing metal, but also ceramic and polymers. And we have a platform called Calypso dedicated to the hot isostatic pressing process in Grenoble. So with that, we address the following technology in metal additive manufacturing. And CEA is really conducting research in order to control and master the link between the raw material, the process, and the final properties of the material, and to ensure in-service performance of AM components. And for that, CEA is involved in all the stages of the processes, from design and simulation to component testing and codification activities. So, if we're talking about opportunity brought by IM in the nuclear sectors, knowing that additive manufacturing concepts start from the 80s, it has really progressed in the past years, and it now offers repeatability, productivity that make it a real manufacturing tool for the nuclear industry. Even though additive manufacturing competitiveness is not the norm compared to forged processes, there is a variety of components where it can decrease delay and cost. And this is particularly true for complex shape, where you can reduce the number of assembly steps. Additive manufacturing also offers additional degrees of freedoms in terms of design of components, and as such you can optimize the topology of the objects, and you can perform also functional optimization. And for the nuclear industry, clearly additive manufacturing can be an opportunity to address long-time operation, because you can use it for maintenance optimization and management of obsolescence of mechanical components. Another key point is that additive manufacturing is quite automated in the fabrication phase, meaning that you can create quite rapidly additional capacity of production in a sovereign and localized manner. And last but not least, it is an additive process by design, meaning that it reduces the requirement in terms of raw materials, and hence it reduces the environmental impact of this process, this manufacturing process. So the deployment of additive manufacturing is already underway. There are some components that are already in use in power plants. These are unclassified components at ISO design with their forged counterparts, but that's already a reality. And there are numerous qualification projects which are ongoing at the national level and internationally. And it starts again with unclassified components at ISO design, but progressively the complexity will increase. And in the meantime, we have also specific components which are designed for Gen 4 reactors and fusion reactors, as it is illustrated by the full assembly grid made at CEA, which was for a sodium nuclear reactor, which was made in 316L. And the real advantage is that with additive manufacturing, you don't have to weld all the strip on the hexagonal plate. So this is really an efficient process for this kind of parts. So now that I will leave the floor to Jacques, who will present the key result of ARQANE project, which is just ending this year.
Good afternoon, everybody. So thanks, first of all, Stephanie and the CEA for this opportunity to present the ARQANE project as coordinator of this project, which the CEA give a huge representation and a lot of works to give a little focus on what is the ARQANE project. So it's 11 key stakeholders leading all the nuclear value chain of the French team, as we say, in a main goal to contribute to qualifications of additive manufacturing of nuclear components manufactured by AM. So the ARQANE project is a joint effort of more than 100 people for less than 5 years. It's just finished a month right before. And the main goals, the first goal of this project at the beginning of the project were to test, to give testing campaigns and to create technical documentation to perform the additive manufacturing for metal typical metal pieces in nuclear field. To go to qualification processes for additive manufactured nuclear components, and finally to have a draft of a unified technical framework. Those was the main objectives of the ARQANE project. To give a little focus on the key achievements of this project, I will firstly talk about the first technology approach by the ARQANE project, the LPBF. So with Jean-Christophe, where you will give him some question after. And we will, after that, focus on the second complementary process of additive manufactured process, which is the wire arc additive manufacturing. So to start with key achievements of the LPBF, the main idea of the project is as a consortium of main nuclear sector and naval actors of French team, were to prove and to demonstrate the quality of additive manufacturing in nuclear components, which those 4 first use cases that all have a certain coherence between them. We have first of all a thin structure, which is the Gaia grid from Framatome, which gets to TRL9 outside project. We've had dual use cases with an alternate grid and an universal hybrid part from TechnicAtome and Naval Group. We've had the opportunity to see the remanufacturing duplicated parts with valve internal part replacements given by EDF. And the manufacturability of a really complex part with a mixing turbine in inox 304L given by Orano. To continue with the other technology focused by the ARQANE project, which is the WAM, we've had 4 others use cases in the same way. So you will recognize this piece here because it's like the opportunity of additive manufacturing is also about hybrid manufacturing. So to see how components that were just created by one way, one technology way, we can give it by hybrid manufacturing. So a part of this piece was created by LPBF, so that's why it was in the use case before, in the slide before. And this higher part of this part is created by wire arc additive manufacturing. The opportunity of this technique that is derivated by the welding process is to create high deposits with the second use cases. We've had the opportunity of high volume of metal deposition, and with all of the idea of the forged near-net shape of wire additive manufacturing, which is the use case of Naval Group. And finally, we've had a use case from Orano, which with the approach of using a quaternary gaze to manufacture parts with wire arc additive manufacturing. Sorry. To give a little focus on a huge part of shared studies, because the idea of the project ARQANE is also to develop the known of those additive manufacturing technologies. So there were a lot of studies, of shared studies, with a lot of collaboration between partners, and most of all were led by the CEA. I won't get too much in the details for this slide because it's most of the things that presented previously Stephanie about all the opportunities and things to continue to develop, to scale up about the processes of additive manufacturing. And then a main key achievements of the ARQANE project is the contribution to qualification of nuclear components manufactured in additive manufacturing. The idea is that ARQANE project just permits to give not only a draft of a unified framework for the nuclear French industry, but the first version of this qualification framework. And thanks to the opportunity of the synergy with the de facto project, which I think we have some representatives here, that is led by EDF and Framatome. Those last ones submitted modification request to the RCCM in September 2025 with this synergy between the de facto project and the ARQANE project. This is my last slide. The idea is that this project permits a lot of work with partners in really close collaboration to address a lot of technical challenges during a lot of time. And so we hope that all of this work will be useful to lead the French team to give the additive manufacturing a place in the manufacturing processes such as forge and machining.
Thank you, Jack, for this overview of ARQANE project. So, as you have heard, a lot have been made. The additive manufacturing is now entering the code. So I will now just highlight some remaining technical challenges that we need to collectively address and emerging opportunities for the future of the nuclear industry. So first of all, if you want to really leverage the degrees of freedom offered by additive manufacturing, you need to develop some new tool and design processes. First of all, you may transition from boundary representation modeling, meaning you define an object by its shape, to functional representation modeling, meaning that you define an object by implicit functions, such as the stiffness gradient, the roughness of the surface, or things like that. And this really opens the doors to innovative design. Secondly, you need to develop tools and processes to iterate between multi-physics simulation, design optimization, and experimental calibration. And last but not least, the design tools and processes must help the designer to integrate the manufacturing constraints at the design phase. And in the following slide, I will present an example of such design constraints. So, this is surface post-processing. At CEA, we have started to work on chemical surface polishing of complex nuclear parts, which incorporate inner channels. And for that, we use a microtomography to monitor the removal of particles and to measure inner channel diameters. From the first lessons that we have learned from our studies is that at the design phase, you need to add another quantity of material of about 0.2 millimeter in order to support this process and preserve the shape of the part. And we think that the average roughness targeted is about 1 to 3 micrometers. And from our initial study, where we show that the surface post-processing efficiency depends on chemical parameters, we see that if we optimize the temperature of the chemical bath, if we optimize the fluid circulation and the efficiency of the hydrogen removal, then we can achieve a roughness average between 2 and 4 micrometers. But this is still a low maturity process, estimated about TRL2, and the remaining challenges are to develop a reproducible process at scale 1 of the component. And for that, we need to control also the chemical bath parameters. And also, we need to evaluate the impact on thermohydraulic properties of this process compared to the forged counterpart piece. A real opportunity brought by IM is also to develop smart materials. So at CEA, we develop two types of sensors: optical fiber sensors and luminescent markers. optical fiber sensors like bright gratings enables to monitor the temperature, the pressure, the deformation, or the vibration all along the fiber lengths. And for that, we have two examples here. The first one, a divertor component, where we measure the temperature at the interface between the tungsten, the 316L, and the copper chrome zirconium layers to monitor the metallurgy process. And on the metal damper example, we monitor the deformation of the damper during a characterization process with different shock testing. And for the luminescent marker, you can either deposit the markers in a layer in the bulk of the material or at the surface. And with this type of sensor, you can follow corrosion or wear detection. A key challenge which is still to address to foster AM adoption is to enhance the knowledge of AM material behavior. And this is, for that, you need to have statistical knowledge, and this will support justification, standardization, optimization of component design and qualifications. So for that, you need to multiply the number of test samples like the one illustrated above and to collect a lot of data. And concretely, what you want to obtain at the end is an envelope values of the material behavior for a given IM specification. And you need to cover different powder supplies, different parametrization of the machine and strategy of manufacturing to ensure that you stay in the envelope value. And another key point is to develop specific additive manufacturing reference technical specification, RTS, of components, or the demonstrations that the existing RTS are applicable to additive manufacturing parts. And this knowledge of AM behavior must also be addressed in the environment of a reactor, meaning with high temperature, irradiation, and potentially a corrosive environment. And finally, you need to characterize the bulk material, but also local geometric singularities like fin walls. And last but not least, if you want to use additive manufacturing in the nuclear industry, we need to address large components. And this is especially true for LPBF technology. And there, the key challenges are to ensure the repeatability and homogeneity of the material characteristic in the full building volume. When you go into large machine, you usually use several lasers simultaneously with overlapping areas, and you have very complex gas flow management. So this is key to demonstrate repeatability and homogeneity. Then you need to demonstrate the transferability from small to large IM platform if you want to leverage past experience. And it is essential to explore opportunity to accelerate qualification, meaning that you want to perform characterization on a limited set of conditions or area of interest while demonstrating the performance of the material on the wall size. And for that, Nikon SLM is the key player in Europe in large to ultra-large LPBF. They already commercialize the NXG, which offer a production volume of 600 by 600 by 1,500 millimeters. And they are developing at the moment a greater than 1 meter cube volume size machine. That is why today CEA and Nikon SLM announced that to address large dimension and the increase of knowledge of IM material behavior, we create MANTRA. MANTRA is a Metal Additive Nuclear Technology Research Alliance. It's an innovation hub on LPBF dedicated to the nuclear sectors. So Nikon SLM and CEA are founders and as such are core members, and design office, manufacturing industries, operation, maintenance industries can come and join the hub to mutualize resources to address the topic I mentioned before together. In parallel to the common project, we are also supporting specific projects between one associated members and the core members, for instance, to develop in a confidential way an innovative components. And the hub will also rely on technology provider like spotter supplier, printing service, post-processing, and so on. So in the first years of the hub, we will focus on 316L material. And the hub is targeted to start early in 2026. So join us to accelerate the adoption of metal additive manufacturing among nuclear companies by collaborating on real-life components and pioneering large-scale machine equipment. So that's the end of my presentation, but obviously I would like to give the microphone to Jean-Christophe, so that Jean-Christophe can share with us the roadmap of Nikon LSLM on large machine and broader than that.
Thank you, Stephanie. Thank you very much. So yes, the large envelope, when I joined Nikon SLM 5 years ago, nobody was talking about parts bigger than, let's say, a screen. And today we are working on parts that are bigger than 1 cubic meters. For those of you who attended the Paris Air Show, the Salon du Bourget in June, on the Safran booth, we presented the part that was almost 1 meter diameter and built on one prototype that we are developing. So the roadmap or what is coming already today available are the machines that Stephanie presented in dimensions, the NXG 600. But bigger volumes are coming, and I think also better in situ monitoring or self-qualification of the machines is coming, and it's coming soon. It's not like 10 years ago. We are working on it, so that in a relatively near future, my vision is that the machine will be able to deliver a certificate of conformity like you get from the forge or like you get from the casting, as we build the material together with the part. The problem of the adoption of the technology today is that there is no certificate of conformity. And I believe that we are on our way, especially on large envelope, which are really the developing a new market and a new need, on our way to have machines that will be able to print in confidence material for nuclear industry, but also for other industries. The aerospace industry, and so especially jet engine manufacturers, have adopted the technology a little bit earlier than the nuclear industry, and they are at the moment, for most of them, getting into serial production. That means the parts, some parts are certified, and I'm talking about flying parts, not so critical, not yet turning parts, but flying parts inside the engine that are critical. And for me, of course, the nuclear industry, the nuclear code, I'm not an expert at all, has some specificities, but at the end, the engine should not fail, right? You cannot accept the engine will fail. The consequences are not as critical when the power plant will fail, but the risk zero is also the norm. And I believe that what the Safran of the world have already done, we can do the same, and we will do the same with Mantra, so that all the industry, the nuclear industry, will be able to use this fantastic technology to develop the next generation of power plant in confidence. So that's really, in few words, the vision, and it's more advanced than one people could think. The state of the art of the technology with Nikon SLM at least is really ready for production. So just be ready. Framatome, we are working a lot with Framatome, who's leading the adoption of the technology in France. Of course, with CEA, and hopefully we will bring with us everyone.
Thank you, Jean-Christophe. Thank you to all of you. We can carry on the discussion because we wanted to say a lot more things. So if you want to join us on the room aside, you're more than welcome. Thank you.